Linear Algebra, Lecture 10. And what we are studying are inner product spaces. I began to talk about this in Lecture 9. I'm going to start from the beginning or review what we've done. So suppose we have vectors x, x1 up to xn in Rn, and y coordinates y1 down to yn in Rn. The standard inner product on Rn is the product of these two vectors, and it's written as x comma y in parentheses, is you sum up the products of the corresponding coordinates, x1, y1, x2, y2, x3, y3, up to xn, yn. So if x is 1, 2, 3 in R3, and y is 4, 5, 6 in R3, then the inner product of x and y is 1 times 4 plus 2 times 5 plus 3 times 6. That's 4 plus 10 is 14 plus 18 is 32, for example. And that's the standard inner product. That's sometimes called the dot product. And in calculus or physics, it's sometimes written as x dot y. But we don't use this notation, this terminology. This is just the standard inner product. In general, if you have a linear transformation T, suppose that V is a real vector space. That is a vector space over the real numbers, not necessarily Rn. A linear transformation T from V to R is called a linear functional. And if you have two vector spaces, that V and W be vector spaces over R, V times W, this is the set of all ordered pairs V comma W, where V is a vector in V, and W is a vector in W. And a bilinear form or bilinear functional, there's two words for the same object, is a function f from V cross W into R, which satisfies the following two properties, such that for all vectors V and V prime in V and W, W prime in W, f of V plus V prime comma W, that's in V cross W, is f of VW plus f of V prime W, and f of scalar times V comma W is the scalar C times f of VW. So if you hold the second vector constant and just look at this as a function of the first coordinate, this is a linear functional. It's a linear transformation. And also, if you hold the first coordinate fixed, and you look at this as a function of the second coordinate, f of v comma w plus w prime is f of vw plus f of vw prime, and s of v scalar times w is the scalar times f of vw. So that's what is called a bilinear form. And the function, f from v cross w into r is symmetric. Let's see, I don't know if this is so well. Suppose we take v cross v. So the first and second coordinates of the ordered pairs are from the same vector space V. A function from V cross V into R is symmetric if f of v, v prime is f of v prime v for all v and v prime in the vector space V. And we say that this function, this is positive definite if f of v comma v, it's a real number, but it's always positive for all vectors v not equal to 0. So the standard inner product is a bilinear form that is symmetric and positive definite. And in general, so this is the important definition, we want to extend the idea of the standard inner product in Rn to an arbitrary real vector space. So an inner product this is the definition on a real vector space V is a bilinear form from V cross V into R that is symmetric and positive definite. And we can see that the standard inner product on Rn has these properties, because if you take x to be the vector x1 down to xn, and y to be the vector y1 down to yn in Rn, the inner product of x and y is the sum of the products of the corresponding coordinates, xi, yi. But xi, yi, these are real numbers. Xi, yi is the same as yi, xi. So this is yx. So this proves that the standard inner product is symmetric. And if the vector x is not the 0 vector, then at least one coordinate is different from 0 for some I. And so if you take the inner product of the vector x with itself, this is summation xi times xi. I goes from 1 to n, which is summation xi squared. I goes from 1 to n. And xi squared is always non-negative. So this is a sum of non-negative numbers. And if at least one coordinate is different from 0, so at least one of these numbers is strictly positive, so this is positive. So this proves that the standard inner product is positive definite. Let's look at another example, of an inner product other than the standard inner product. If we take V to be C01. This is the set of all continuous functions f from 0, 1 into R. Right? So 0, 1, all continuous functions, y equals f of x. And define fg to be the integral from 0 to 1 of f of x, g of x, dx. So I claim this is an inner product. This is just integration. You integrate the product of the functions. So if I take f plus, let's say f plus f1 plus f2, comma g, that's the integral from 0 to 1 of f1 plus f2 times g dx. But you learn an integration, so this is the integral from 0 to 1. Actually, f1 of x, g of x, plus f2 of x, g of x, dx. But that's the integral from 0 to 1 of f1 of x, g of x, dx, plus the integral from 0 to 1, f2 of x, g of x, dx. And that's the inner product of f1 and g. And this is the inner product of f2 and g. And it's also clear f times g is the same as g times f, so this is symmetric. And if you take the inner product of f with, well, I mean, let's check scalar multiplication. So cf times g is the integral from 0 to 1, cf of x, g of x, dx. But you can always take a constant outside the integration sign. This is c integral from 0 to 1, f of x, g of x, dx, which is c times fg. And if I take fg, which is the integral, f of x, g of x, again, multiplication is commutative. This is the same as the integral from 0 to 1, g of x, f of x, dx, which is the inner product of g and f. So this is symmetric. And if I take the inner product of f with itself, that's the integral from 0 to 1 of f squared of x dx. F is continuous. This is always non-negative. If f is not identically 0, this is positive somewhere. So it's positive in some small interval. And this is greater than 0 if f is not a 0 function. So we have positive definite. So integrating the product of two functions is an inner product on the real vector space of C01 of continuous functions from 0 to 1. So that's a nice example to keep in mind. So you have a second example other than the standard inner product in Rn. With the inner product, we can define the length of a vector v. If v is different from 0, then we know that the inner product of v with itself is positive, and you can take the square root of a positive number. So we define the length of v as the square root of the inner product of f with itself. And of course, this is exactly what you know is the length of a vector in R2 and R3. So for example, if v is the vector xy in R2, then when you take the inner product of v with itself, you get x times x plus y times y, which is x squared plus y squared. So the square root of the inner product is the square root of x squared plus y squared. That's the length of the vector v, which is exactly what you learn in calculus or pre-calculus. This is x and this is y. By the Pythagorean theorem, the length of this line from the origin to the point, that's the hypotenuse is exactly square root of x squared plus y squared. So this is consistent with the definition of length that you get from the Pythagorean theorem. So once you have an inner product, you actually have a way to define the length. And in fact, you can go in the opposite direction. Once you have the length, you can actually deduce the inner product. So this is theorem 1. It's something called the polarization identity. It says the following: if you have a real inner product space, the inner product of x1 and x2 can be expressed in terms of the length of vectors. It's 1/4 the length of the vector x1 plus x2 squared minus 1/4 the length of the vector x1 minus x2 squared. So inner product determines length, but length also determines inner product. This is, we have V in inner product space, and x1, x2 are vectors in V. So let's see. What is the proof of this? So x1 plus x2 squared, this is just the inner product of x1 plus x2 with itself. So we can expand this using the bilinearity. This is x1 inner product with x1 plus x2 plus x2 times the inner product of x1 with x2. If we expand this, we get x1, x1 plus x1, x2 plus x2, x1 plus x2, x2. And because x1, x2 equals x2, x1, this is x1, x1 plus 2, x1, x2 plus x2, x2. And if I look at the norm of x1 minus x2 squared, that's like the norm of x1, or this is the length, x1 plus minus x2. So this is x1, x1 plus 2, x1 minus x2 plus minus x2 minus x2. Right? I'm just using the fact that x1 minus x2 is x1 plus minus x2. So I'm using this identity, replacing x2 with minus x2. This is x1 comma x1. The minus sign comes out. Minus 2, x1, x2. Minus comes out, minus comes out, minus times minus is plus, plus x2, x2. So let me just write down again what I calculated. X1 plus x2 squared is x1, x2 plus 2 x1, x2, so x1, x1, plus x2, x2. And x1 minus x2 squared is x1, x2 minus 2 x1, x2 plus x2, x2. So if I subtract the length of x1 plus x2 squared minus the length of x1 minus x2 squared, these cancel and these cancel, and I get minus minus 2. This is 4 times the inner product of x1 and x2. So if I just divide by 4, x1, x2 is a fourth the length of x1 plus x2 squared minus a fourth the length of x1 minus x2 squared. And that's the end of the proof. This is the polarization identity. Now, suppose we have V, a real inner product space. When we talk about inner product spaces, that is vector spaces with an inner product, we only are using vector spaces over the reals or vector spaces over the complexes. The definition of an inner product over the complex and a vector space over the complex numbers is a little different, and we're not going to deal with that in the summer school class. So all vector spaces are real. That means vector spaces over the field of real numbers. And recall that a linear operator is a linear transformation T from a vector space to itself. And we say that a linear operator is orthogonal if it preserves the inner product. If for all vectors v and w in the vector space V, you can take v and w and compute their inner product. You can also look at t of v and t of w and compute their inner product. And if these are equal for all v and w, this linear operator, this linear transformation from V to itself, is called orthogonal. So you might say, I'll put this in quotes, an orthogonal operator preserves the inner product. Right. You have the inner product of v and w. That number doesn't change if you take the inner product of t of v and t of w. Now, an orthogonal operator, if it preserves the inner product, it also preserves the length of a vector, because the length of the vector v is the square root of the inner product of v with itself, which is the square root of the inner product of t of v with itself. Because an orthogonal operator preserves the inner product, but this is the length of t of v squared. So that's the length of t of v. So if you have an orthogonal operator, it preserves the length of a vector. So you can sort of think of this, if you like, geometrically. Let's say you have circle of some radius r, and you have some vector v on the circle, and you have an orthogonal operator. All it can do is move it around the circle, because if the length of v is r, then the length of t of v is r, if t is orthogonal. So orthogonal operators move vectors from one place in the vector space to another, but they always say the same distance from the origin. The length doesn't change. And you can also say that if a linear operator t from v to v preserves length, which means the length of v is the length of t of v, for every vector in the vector space V, then T is orthogonal. Because by the polarization identity, the inner product of V and W is a fourth the length of T of V plus, sorry, is a fourth the length of V plus W squared minus the fourth the length of V minus W squared. But T preserves length, so this is the same as 1/4 the length of T of V plus W squared minus a fourth the length of T of minus W squared. But because T is linear, T of V plus W is T of V plus T of W. And T of V minus W is T of V minus T of W. And again, by the polarization identity, this is exactly the inner product of T of V and T of W. So if a linear operator preserves length, then it also preserves the inner product, and so is orthogonal. So you can also define, if you wish, an orthogonal operator as one that preserves the length of vectors. That's an example of an orthogonal operator. So in R2, let R alpha be rotation by alpha radians. That means if you have any vector V, if you translate it, rotate it by around the origin by an angle alpha, you get T alpha of V. And the matrix for T alpha, or R alpha, sorry, R alpha is what I'm calling it, rotation by alpha, is cosine alpha, sine alpha, minus sine alpha, cosine alpha. And I claim that R alpha is an orthogonal operator. So suppose I let V be the vector xy in R2. R alpha of V is what? It's this matrix cosine alpha, sine alpha, minus sine alpha, cosine alpha applied to the vector xy. So when you rotate the vector xy, you get a vector whose coordinates are x cosine alpha minus y sine alpha, x sine alpha plus y cosine alpha. And what is the length of R alpha of V? Let's take the square of the length. It's the sum of the squares of the coordinates. X cosine alpha minus y sine alpha squared plus x sine alpha plus y cosine alpha squared. So let's square this. This is pre-calculus. X squared cosine squared alpha minus 2xy cosine alpha sine alpha plus y squared sine squared alpha plus x squared sine squared alpha plus 2xy cosine alpha sine alpha plus y squared cosine squared alpha. We're adding, these cancel. I get x squared times cosine squared alpha plus sine squared alpha plus y squared times sine squared alpha plus cosine squared alpha. Sine squared plus cosine squared is 1. So this is x squared plus y squared. So that's the length of v squared. So r alpha of v has the same length of v as v for every vector v. So rotation is a very beautiful classical example of an orthogonal linear operator. So let V be a real inner product space. That means it's a vector space over the real numbers with an inner product. And we say that vectors E1 and E2 are orthogonal if their inner product is 0. Let's say non-zero vectors are orthogonal or perpendicular, which is always a synonym for orthogonal, if the inner product is 0. And a set of vectors, E1, E2 up to En, is orthogonal if they're all different from 0 and the inner product of any two of them, Ei, Ej, is 0 whenever I is different from j. I strictly less than j. So a set of vectors is orthogonal if they're pairwise orthogonal. The inner product of any two of them is 0. And we say the set of vectors is orthonormal if E1 up to En is orthogonal. So these are non-zero vectors that are mutually perpendicular, and they all have length 1. The length of E sub I is 1 for all I. So an orthonormal set of vectors is a set of vectors of length 1 that are mutually perpendicular, mutually orthogonal. I should note that a vector U is called a unit vector if the length of U is 1. So a unit vector is just a vector of length 1. And a unit vector is a vector of length 1. If V is any non-zero vector, then I claim that if I take V divided by the length of V, this is a unit vector. Why is that? So V is not 0, so its length is strictly positive, so I can divide by it. And what is the length of V over the length of V? Let me take the length squared. That's the inner product of V over the length of V, comma V over the length of V. I can take a scalar outside. This is 1 over the length of V, the inner product of V, and V over the length of V. But I can take this scalar 1 over V outside. That gives me 1 over the length of V squared, inner product of V with V. But this is just the length of V squared over the length of V squared, which is 1. So any vector divided by its, any non-zero vector divided by its length is a unit vector. And an orthonormal set of vectors is a set of vectors that is orthogonal and orthonormal. Now, if V1 up to Vn is an orthogonal set of vectors, then if we let u sub I be Vi over the length of Vi for all I, so these are then unit vectors. And I claim then that u1 up to un is an orthonormal set of vectors. And it's easy to see why, because for I different from j, the inner product of ui and uj is the inner product of vi over the length of vi with the vector vj over the length of vj. You can take scalars outside the inner product. That's 1 over the length of vi, 1 over the length of vj, the inner product of vi and vj. But this is 0 because the v's are orthogonal, so you get 0. So you can always transform an orthogonal set into an orthonormal set simply by dividing each vector by its length. And one nice property of orthonormal sets is that it reduces every inner product on a finite dimensional vector space to the standard inner product. So this is could be a theorem or a lemma. We have V, an n-dimensional vector space. And suppose that F1 up to Fn is an orthonormal basis for V. That V and W, the vectors in the vector space, if you write each of them as a linear combination of the basis vectors, so if V is summation xi fi, I goes from 1 up to n, and W is summation yi fi, I goes from 1 up to n, then the inner product of V and W is just like the standard inner product. It's summation xi yi, I goes from 1 up to n. So this is very natural formula for the inner product of two vectors if they are if you know their coordinates with respect to an orthonormal basis. And the proof of that is just a straightforward consequence of the definition of bilinearity. So we have V is summation xi fi. I goes from 1 up to n. Let's say W is summation, let me use j as an index, yj fj, j goes from 1 up to n. So the inner product of V and W is summation It's the inner product of summation xi fi. I goes from 1 up to n. Summation yj fj. J goes from 1 up to n. If I expand this just by using bilinearity on the first sum n, this is summation I goes from 1 up to n. xi, inner product of fi, with summation yj fj. J goes from 1 up to n. Using the bilinearity of the inner product with respect to the first coordinate. But we also have the bilinearity of the inner product with respect to the second coordinate. So this is summation I goes from 1 up to n, x sub I, f sub I, summation yj fj. This is summation j goes from 1 up to n, yj, inner product of fi and fj. So I have a double sum. I goes from 1 up to n. J goes from 1 up to n. Xi, yj, fi, fj. This is the inner product of fi and fj. But the inner product of fi and fj, if these vectors are orthonormal, this is 0 if I is different from j. And if I equals j, that's just the length of fi squared, which is 1. So it's 0 if I is different from j, 1 if I equals j. So another way of writing that is this is delta ij, where this is our favorite Kronecker delta. It's just the function which is 1 if I equals j and 0 otherwise. So this is summation I goes from 1 up to n, j goes from 1 up to n, xi, yj, delta ij. The only time this is not 0 is when I equals j. So this is summation I goes from 1 up to n, xi, y sub I. And that's what we wanted to prove. So when you have an orthonormal basis and you express vectors with respect to that orthonormal basis, then it's easy to compute the inner product. And there's one other extremely important use of the inner product. And again, if you've taken Calc 3 or elementary physics, you're familiar with this idea. So suppose you have vectors v and w. These are non-zero vectors. In the vector space V. So let's say here is V and here is W. And you can always decompose V so there exist unique, existence and unique vectors V1 and V2 such that V1 is parallel to W, V2 is perpendicular to W, and V is W1 is V1 plus V2. So we have, here's my vector V, and there's a piece V1 parallel to W, a piece V2 perpendicular to W, and V is V1 plus V2. Remember that V and V2 and W are, or V1 what does it mean to say two vectors are parallel? If one is a scalar multiple of the other, and V2 and W are perpendicular, if either one of them is 0 or the inner product of V2 and W is 0. So that's the definition of parallel and perpendicular. Two vectors are parallel if one is a scalar multiple of the other, and two vectors are perpendicular if their inner product is 0 or if they are orthogonal. So this says you can always decompose it. When you have two vectors, V and W, you can always write V as a sum of a vector parallel to W and a vector perpendicular to W. And the component V1 parallel to W, V1 is called the projection of V onto W. So the projection of a vector onto another vector is a vector parallel to that other vector, and that decomposes in this way. How do we do this? So this is a construction. This is a lemma, if you like. But I'm actually going to give a formula for how you write down these vectors V1 and V2. So it's a little bit easier to start if we take a unit vector in the direction of W. So let U be the vector W divided by its length. So this is a unit vector parallel to W, or in the direction of W. And suppose I let V1 be the inner product of V and U times the vector U. So U is a vector, this is a scalar, so V1 is a scalar multiple of U. So V1 is parallel to U, which in turn is parallel to W, so V1 is parallel to W. So suppose I let V1 equal that, and let V2 be equal to V minus V1. So let's make one obvious statement. V is V1 plus V minus V1, because the V1s cancel. That's V1 plus V2. So V is certainly the sum of the vectors V1 and V2. I know V1 is parallel to U, must show that V2 is perpendicular to W. So V2 perpendicular to W. V2 is V minus V1 in a product with W. Let's see. This is V minus V1 V1 was the inner product of V with U and U. Oh, sorry. Let me just start to write out the equation, see what happens. So V minus V1 inner product with W is VW minus V1W. So this is VW, inner product of V and W, minus V1. V1 is the inner product of V and U times U, inner product with W. It's the inner product of V and W minus, and U, what is U? U is W over the length of U. So this is the inner product of V and W over the length of W times U, which is W over the length of W, inner product with W. Let me put this on another piece of paper so I don't have to squeeze it in so tightly. So here's my picture. Here's W. Here's V. I want to write V as the sum of a vector V1 plus the sum of a vector V2. So I let V1 be the inner product of V and U with U, or a unit vector in the direction of W, U, is W divided by the length of W. So I could write this as, this is V, W over the length of W times U, which is W over the length of W. So this is, if I take out these scalars, 1 over the length of W squared, the inner product of V and W, so this is all a scalar. Okay, this is a number, times the vector W. I'm going to let V2 be V minus V1, and I must show that V2 is perpendicular to W, that the inner product of V2 and W is 0. So let me do that calculation. The inner product of V2 and W is the inner product of V minus V1 and W. That's VW minus V1W. V1 is this scalar times W times W, inner product with W. That's the inner product of V and W minus, I have, this is the length of W squared over the length of W squared times the inner product of V and W. But this is 1. This is just VW minus VW, which is 0. So we're done. So I proved, so therefore, there exist vectors V1 and V2 such that V1 plus V2 is V. V1 is parallel to W. V2 is perpendicular to W. Moreover, the V1 and V2 are unique. There's only one way to decompose them in this way. And let's see if we can prove uniqueness. So suppose V is V1 plus V2, and also V1 prime plus V2 prime. Where V1 and V1 prime are parallel to W, and V2 and V2 prime are perpendicular to W. So if we subtract, rearrange this equation, we get V1 minus V1 prime is V2 prime minus V2. let's call this vector v star. So v1 minus v1 prime, these are both parallel to w, so the difference is parallel to w. And v2 prime minus v2, if I take the inner product of that with w, that's v2 prime w minus v2w. Each of these is perpendicular to w, so each of these inner products is 0, and 0 minus 0 is 0. So v2 minus v2 prime is perpendicular to w. So this vector v star is simultaneously parallel and perpendicular to a vector. How is that possible? So I claim this implies that v star is 0. And so if v star is 0, v1 equals v1 prime, and v2 equals v2 prime. Okay, let's see, why is that? So v star parallel to w implies v star is some scalar multiple of w. There's some scalar c. V star perpendicular to w means v star and v, the inner product, is 0. But, sorry, v star and w, the inner product is 0 because v star is perpendicular to w. But v star is c times w. And if I take out the c, that's c times w, inner product with itself, c times the length of w squared. But w is a non-zero vector. So therefore c equals 0. So therefore v star equals 0. So this decomposition of a vector into a component parallel and another component perpendicular to w is unique. This is all the basic geometry of inner product spaces. Let's take an example. So this is an example in the text. Suppose I take v equal to vector 3, 2, and w be the vector 7, 3. So 2, 3, 4, 5, 6, 7, 1, 2, 3. So 7, 3 is here. This is w. And 3, 2 is here. So this is the vector v, and this is the vector w. And I want to find components of v. v1 is this component, parallel to w, and v2 perpendicular to w. Okay. So what was our formula? Our formula said that v1 be the inner product of v and w divided by the length of w squared. If w is 7, 3, the length of w squared is 7 squared plus 3 squared, which is 49 plus 9, it's 58. the inner product of V and W is 3 times 7 plus 2 times 3. 21 plus 6 is 27. So this is 27 over 58, sorry, times the vector W. So V1 is 27 over 58 times the vector W, 73. So if you work that out, this is 7 times 27 is 189 over 58. That's the first coordinate. Second coordinate is 81 over 58. That's the vector V1. And V2 is V minus V1. That's 3, 2 minus 189 over 58, 81 over 58. See, if I put everything over a common denominator of 58, 3 times 58 is 176 over 58. 2 times 58 is 116 over 58. Minus 189 over 58. 116 over 58. Sorry. 180 minus 81 over 58. When I subtract, I get, let me see if I did my work. This is 184. Minus 15 over 58. And this is 116 minus 81, which is 35 over 81. So that's the vector V2, and this is the vector V1. If we just want to check, it's supposed to be that V2 is perpendicular to W. So let's take their inner product. It's supposed to be the inner product of V2 and W. That's the inner product of minus 15 over 58, 35 over 58. With the vector W, which is 7, 3. So this is minus 7 times 15 over 58 plus 3 times 35 over 58. And you can check, this is 105 minus 105 is 0. So this calculation is all fine. And again, if it's hard to read in my handwriting, this is all in the chapter on inner product spaces that I posted already. Now, orthonormal bases, this is just sort of a moral lesson. Orthonormal bases are good. So, given a basis, B for a vector space, construct from it an orthonormal basis. Orthonormal basis. That's what we have to do. So there is a method called the Graham-Schmidt SCHMIDT ortho normalization process. Or if you like computers, you can call it an algorithm. This is a step-by-step way, given a basis, to construct from it an orthonormal basis. And you can observe first, it suffices to construct an orthogonal basis. And the reason is, once you have your orthogonal basis, take each vector, divide by its length to get unit vectors. And you have an orthogonal basis of unit vectors, which is the definition of an orthonormal basis. An orthonormal basis is a set of vectors linearly independent and spanning the space, which are mutually orthogonal, and they're all unit vectors. They all have length 1. And we're going to do it step by step. We're going to start with a set of orthogonal vectors, and then add another vector which is orthogonal to get a larger set of orthogonal vectors in your vector space. And the crux of it is the following lemma. So we have sort of a picture like this. Here's my vector space V. Inside of V, so this is my vector space. Inside of V, we have a subspace W. And in W, you have, so we have, let's say the dimension of W is K. And suppose we have W1 up to WK, an orthogonal basis for W. So sitting inside of W, we have these K vectors, which are linearly independent and span the subspace. Every vector in W is a linear combination of the vectors in the spaces. And these are orthogonal. They're mutually perpendicular. The inner product of any two different ones of these is 0. We don't assume that these have length 1 yet. We don't have to. All we care about is that they're orthogonal. Suppose I take another vector, W prime, which is in V, but not in W. So W prime is outside of W. And I can let W prime, let capital W prime be the subspace of V generated by the set of K plus 1 vectors, W1, W2, up to WK, and this new vector W prime added. Now, the subspace W prime, it contains W1 up to WK, so it certainly contains the whole subspace W, but it also contains W prime, which is not in W, so W prime is a strictly larger subspace of V than W. And we proved, so this is an old theorem, it was even a test question, this set is linearly independent. So this set of K plus 1 vectors is linearly independent. Because if it were linearly dependent, W prime would be a linear combination of W1 up to WK, which means W prime would be inside the subspace W, which it is not. Now I want to get a vector wk plus 1, which is orthogonal to all of these vectors. And parallel to w prime, or not parallel, but is literally independent from w not to wk. So I want to construct wk plus 1 such that wi wk plus 1, that inner product is 0 for all I from 1 up to k, and the set w1 of the wk plus 1 is the basis for this larger set w prime. So I start with an orthogonal basis for w. I have a vector w prime not in w, so that generates a larger subspace. And I want to be able to somehow extend my orthogonal basis for w to an orthogonal basis for w prime. And I'm going to do that by taking w prime and subtracting from it the projection of w prime in the direction of all of these k different vectors w sub I. So I just have to recall what I did a few minutes ago, which is write down how do you find the projection of one vector in the direction of another. So again, let's just review that. Here's a vector v, a vector w, and this vector, which I called v2 before, but this is going to be the projection of v in the direction of w. So this is a vector parallel to w. It is the inner product of v and w divided by the length of w squared times the vector w. So this is a vector parallel to w because it's a scalar multiple of w. And v minus this is perpendicular to w. So this was the formula that we proved in the previous lemma for the projection of v in the direction of w. Now, in this case, we have vectors v1 up to vk in a subspace w, inside a vector space v, and sorry, w1 up to wk, and a vector w prime in v but not in w. So the projection of w prime in the direction of w sub I, so this is for I going from 1 up to k, the projection of w prime in the direction of wi is the inner product of w prime and wi divided by the length of wi squared times the vector wi. So that's for each I, this is the projection of the vector w prime in the direction of wi. And I want to define vk plus 1 to be w prime minus all of these different projections. Summation I goes from 1 up to k, inner product of w prime and wi over the length of wi squared times wi. So from w prime, I construct a new vector wk plus 1. And I claim that wk plus 1 is perpendicular or orthogonal to all of the vectors w sub I. So that's the first thing I want to show. So the inner product of wk plus 1 and wi for all I from 1 up to k That's the inner product of WK plus 1. What is WK plus 1? This is it. I have to write it out. This is W prime minus summation. I goes from 1 up to K. W prime WI over the length of WI squared. That times WI. Let me do this for J. J. Inner product with WJ. What is this? This is the inner product of W prime and WJ minus the sum. I goes from 1 up to K. Inner product of W prime and WI over the length of WI squared. Inner product of WI, WJ. Now this is 0 if I is different from J, because the vectors W1 up to WK are mutually perpendicular, orthogonal. So if I is different from J, this is 0. So the only time we get a non-zero number here is when I equals J. So this is W prime WJ minus, when I equals J, I have W prime WJ over the length of WJ squared, WJ inner product of WJ. But the inner product of the vector with itself is the square of the length. So this equals this. They cancel. I get W prime WJ minus W prime WJ. That's 0. So the K plus 1 vectors, W1 up to W, so K plus 1, this set of vectors is an orthogonal set. And if I take WK plus 1 and W1 up to WK, I can take the linear combination of the W1 up to WK that cancels this. So W prime is in the subspace generated by W1 up to WK plus 1, which is going to be this larger set W. So the moral of the story, and again, there's a lot of algebra involved in this, which is perhaps why we call this course linear algebra, is that if you have an orthogonal set of vectors in a vector space, and you take another vector that's not in the subspace they generate, you can extend your original orthogonal set to a one larger orthogonal set that spans your larger subspace. And this is all we need to prove Gram-Schmidt. So the Gram-Schmidt is called the orthonormalization process or algorithm. It says, let V be a finite dimensional inner product space. So the dimension of V is some positive integer n, with the basis V1 up to Vn. So every vector space of dimension n has a basis with n vectors. So take any basis, fix a basis. There exists an orthogonal basis W1 up to WK for V with the following properties. So an orthogonal basis would be such that first, if I take the first k vectors, up to Bn, the first k vectors of V and the first k vectors of W, they generate the same subspaces for all k going from 1 up to n. Second, there is an orthonormal basis U1 up to UN with the same property. So the first k vectors of your original basis generates the same subspace as the first k vectors of this new orthonormal basis. And the third property is if U1 up to UK is an orthonormal set in V, you can extend it to a basis, then there exist vectors UK plus 1 up to UN such that U1 up to UN is an orthonormal basis for V. Now, to show that 1 implies 2 implies 3 is easy, because if you have an orthogonal basis, take each vector, divide by its length, you get unit vectors, and that gives you the orthonormal basis. So 1 implies 2. Moreover, if you have an orthonormal set in V, you can always just take any other vector not in that set. You can find a UK plus 1 of length 1 orthogonal to these, such that U1 up to UK plus 1 generates this one-dimensional larger subspace. And you add vectors 1 by 1 until you get a basis for V. So the only substantial part of this is to prove the first statement. But effectively, we already proved the first statement. So let's just think about this for a moment. Here we have our vector space V. We have the vector V1. Let W1 equal V1. That's pretty simple, because, and then they're the same. So the subspace generated by V1 is the subspace generated by W1. Now, outside of that subspace generated by V1, we have the vector V2. By the lemma, there exists a vector W2 such that W1 and W2 are perpendicular, and the subspace generated by W1 and V2 is the subspace generated by W1 and W2. Okay. Here's the space generated by V1, called W1, which is the same as the space generated by W1. We have a vector V2. V2 and W1 generate a larger subspace called W2. And there's a vector W2 perpendicular to W1, such that W1 and W2 generate W2. And you just continue. This is just the easy way of saying it, but you have to actually check. Continuing by mathematical induction, we obtain an orthogonal basis for V. And once you have an orthogonal basis, you divide by the length of the vector to get an orthonormal basis. And that is it. But the secret is this first step. It was the lemma that you take a vector, take a second vector, and subtract off the projection in the direction of the first, and you continue. So let me do one example, because I have a little bit more time. So this is an example. Suppose we take R3, and R3 we have the basis of the vectors V1, which is 0, 1, 1, V2, which is 1, 0, 1, and V3, which is 1, 1, 0. So you need to check this is a basis for R3. Okay, so first we want to construct orthogonal vectors. And the first step is easy. Let W1 be V1, 0, 1, 1. That's my W1. What is the next step? W2, you take V2 minus the projection of W1 in the direction of V2. What is the projection of W1 in the direction of V2? It's the inner product of V2 and W1 divided by the length, it's V2 minus the projection of V2 in the direction of W1. The projection of V2 in the direction of the previous vector W1. So that's the inner product of V2 and W1 divided by the length of W1 squared, W1. What is this? V2 is 1, 0, 1. The projection of V2 in the direction of W1, so this is going to be a scalar multiple of W1, 0, 1, 1, some scalar multiple of that. What is that scalar multiple? It's the length of W1 squared. W1 squared is 1 squared plus 1 squared is 2. The inner product of V2 and W1, you get 0 plus 0 plus 1. It's a half. So this is 1, 0, 1 minus a half times this vector, 0, a half, a half. That's the vector 1 minus a half, a half. That's my vector W2. Let's just check. The inner product of W1 and W2 is the inner product of 0, 1, 1, and 1 minus a half, a half. That's 0 times 1 plus 1 times minus a half plus 1 times a half. 0 minus a half plus a half is 0. So this is my vector W2. This is W1, this is W2. What is my third vector, W3? W3 is going to be the vector V3 minus the projection of V3 in the direction of W1 minus the projection of V3 in the direction of W2. So this is V3, 1, 1, 0. The projection of V3 in the direction of W1 is V3 inner product with W1 divided by the length of W1 squared times W1. Let me write this actually over here. 1, 1, 0, or V, let me just write it down. This is V3 minus the projection of V3 in the direction of W1 is V3 W1 over the length of W1 squared W1 minus the projection of V3 in the direction of W2. That's V3 W2 over the length of W2 squared W2. So let's do the calculation. V3 is 110. V3 dot product, inner product with W1. It's 110 dot product, inner product with 011. That's 010. That's 1 over the length of W1 squared, which is 2, times W1, 011, minus the inner product of V3 and W2. So 110 gives me a half over the length of W2 squared. W2 squared, when I square it, I get 1 plus a fourth plus a fourth. That's 3 halves. So it's 1 half over 3 halves times the vector W2, which is 1 minus a half. So this is the vector 110 minus the vector 0, a half. A half over 3 halves is a third. So this is minus a third. A third times minus a half is minus a sixth. And a third times 0 is 0. If I do my arithmetic correctly, I get 1 minus 0 minus a third, which is 2/3. 1 minus a half plus a sixth is 1 minus a third, which is another 2/3. And minus a half plus a sixth is minus 2/3. So this is my vector W3. And then I divide each of these vectors by their lengths, and I get the orthonormal basis. Again, this is all the details are written out legibly in the notes on inner product spaces. So I encourage you to study that. That is it for tonight. Questions?